Hello and welcome to LS Instruments webinar program. This is our first webinar and we're very glad to have you here with us today. We will be focused on the DWS RheoLab and its applications. Before we begin, I would like to mention that this is an interactive webinar and that your questions are welcome and encouraged. You can ask them to us through the chat window that you see on the lower right side of this webinar window. At the end of the presentation, a transcript of your questions and the corresponding answer will be released together with a recording of the webinar. My name is Coline Bretz. I'm the Marketing and Sales Manager at LS Instruments. I joined the company 3 years ago. Before that, I studied fundamental physics and I hold a PhD in physical chemistry. With me today is Dr. Andrea Vaccaro, who is the CTO of LS Instruments. Andrea joined LS Instruments in 2010 and is a chemical engineer who holds a PhD in colloidal science. As we start, I would like to just mention a few words about LS Instruments. We are a Swiss company that was founded about 10 years ago from a spin-off of the Free World University. Our specialty is light scattering technologies, and we specialize particularly in static light scattering, dynamic light scattering, and diffusing wave spectroscopy, DWS, which will be the focus of today. Our goal is to provide our customers with the most advanced and reliable solutions to solve their analytical and research challenges. Our customers are typically industrials, but also academic scientists in more than 30 countries around the world. You can see an example of some of our customers here on the lower end of this slide. And I want to mention also that just last year, we had more than 40 scientific publications released using our instruments. I would like to say a few words about our product portfolio. The first instrument we offer is the LS spectrometer, which is a goniometer-based instrument for dynamic and static light scattering. It can perform particle sizing, particle shape, and molecular weight characterization. It can characterize partially arrested systems, such as gels, and it can do so using the 3D technology for multiple light scattering suppression. The NanoLab 3D is a single-angle DLS instrument that can perform particle sizing. It can perform also microviscosimetry via DLS and microrheology measurements. All of this in concentrated samples while suppressing multiple light scattering. So you can characterize a sample in its natural state without having to dilute it, as is often the case in some systems. Also, the DWS RheoLab, which is the focus of today, as you know, this is an optical rheometer for contact-free viscoelasticity measurements, and it can do so as using the DWS technology. So with this, you can not only characterize the viscoelasticity, but also the stability monitoring processes and perform particle sizing, depending on the kind of samples that you have available. At this point, I would like to show you the instrument. You can now see on the audiovisual pod the DWS RheoLab. You can see that it's a very compact and simple instrument. The interaction with the user is limited to two interfaces. So first you have the on and off button, and you also have this access to the sample chamber that can be slid open. Inside the sample chamber, you can insert a sample. So this is an example of a glass cuvette in which we can insert the sample. So we would load the sample, which can be a gel, a liquid, and anything in between, a viscoelastic sample. We will load this into this glass cuvette, close it, we can seal it, and then insert it back into the instrument. Everything else is performed using our software, which has a very user-friendly graphical user interface. A few words about the types of cuvette that we use. I've showed you here a cuvette that is the largest we offer. So it's a 10 by 10 millimeter cuvette. We can also offer smaller size of cuvettes, depending on the type of sample you want to analyze and also on the quantity of sample that you have available. Here, I'm showing an example of a 2 millimeter size cuvette. You can see how much thinner it is. And we also have 1 millimeter width cuvettes, for which the minimal sample loading volume is 150 microliters. So with this device, you can actually characterize samples and use a very small amount of it. So if you have precious samples, this can be very, very handy for you. Otherwise, just load them in the bigger cuvettes, which holds up to 3 milliliters. You see that it's sealed, so you can perform measurements without any evaporation or contamination, and this is very useful for researchers wanting to characterize the stability or processes going on in the sample at long time, as it can be stored and remeasured anytime. You can also, of course, recover the sample as it's after the measurements. This is also a very big advantage of DWS technology. So let me just reinsert it and close the device back. And at this point, I would like to hand the speech to Andrea Vaccaro, who will talk about the principles behind these instruments.
Hello, everybody. So what is the DWS RheoLab instrument all about? It's about rheology. Rheology is this science that studies the flow and the deformation upon external stimulation of our sample. And why is this this science very important? Is because the way a sample flows or deforms gives very important technological properties to our products. Here you can see several products where the consistency and the ability to flow and deform plays a key role in the way they are perceived and appreciated by the customer. And we can say that all these for all these products there is a very single feature that dictates the rheological properties, and it's the microstructure. Let's take, for example, the example of the paint. For the paint, it's really crucial that the paint has the optimal thickness, because if the paint is too thick, it is very difficult to spread it on the surface. If it is too thin, it flows too easily, then it will drip off from the surface that it is being applied to. If we take, for example, instead the example of the soap, we know that customers enjoy very much products that have a very good texture in their hands, and they are thick. But on the other hand, we don't want the soap to be too thick, to be too difficult to spread on the hands. So the main message here is that the ability to flow and the rheological properties are a key feature. They are influenced by the microstructure of our sample, and it is crucial to study analytically and to determine the rheological property by means of an analytical instrument. So here we see how it is classically assessed, the effect on microstructure on the properties of a sample. Classically, you would use a mechanical rheometer made up of a cone and a plate, would load the sample between the cone and the plate. The rheometer would apply a deformation or a rate of deformation, and then it would measure the response, the force that develops due to the sample being analyzed. Here we see the main feature of a mechanical rheometer. The sample is due to external forces, so we touch our sample. We obtain microscopic information about the sample, and we also have the problem is that by deforming with external forces our sample, we risk to damage the microstructure, which is the feature that we want to assess, that we want to measure. Another feature of the mechanical rheology is that many times, in order to acquire a meaningful set of data, the measurement has to last quite some time, and also each time a measurement is done, if we want to measure another sample, we will have to dispose the old sample. And if we want to measure the old sample, we will have to recreate the old sample and reload. Instead, the DWS Microrheology is an optical method. It's completely contact-free. The measurement are run within a sample that is sealed. no external forces are applied, because it's the particles that are present that scatter light that are going to probe by means of their motion the microstructure. This gives to this technique a very high sensitivity, and it also avoids destroying the sample, the risk of destroying the sample. Another great feature of the DWS microreology technique is that normally a full signal can be acquired in as low as 1 minute and 5 minutes at maximum. So each measurement is very fast. So let's see what is the principle behind the diffusive weightex spectroscopy technique, which allows us to perform microreology experiments. So we see here in this animation our sample in the cuvette. The sample contains some particles that diffuse light. These particles might be part of the microstructure or can be added in case there is not enough signal arising. And we are shining the laser originating from a laser on the sample. Each particle will then rediffuse and rescatter these photons. So each photon emitted by the laser will jump on many particles until it reaches a detector. The detector will record the evolution in time of the intensity scattered by the sample, which is the raw signal that is being acquired. Now, it is clear that at each moment in time, the sample will and the particle will be in a certain configuration, and by diffusing and probing the sample, the scattering pattern will be different in time. So for this reason, we calculate from the recorded scatter intensities as a function of time, our instrument calculates the so-called correlation function. The correlation function is then translated by a simple mathematical equation in the signal that is interesting to the scientist, which is the mean square displacement. The mean square displacement is the square of the path that is being traveled by the particle as a function of time. So it will tell us the ability of our particles to travel within the sample, and this signal allows us to gather a lot of information about the microstructure. If the size of our particles is known, we can then obtain the microreology data, which are the storage and loss moduli that we will see later on, or in case we know that the sample is viscous and we know its viscosity, we can obtain the particle size. So let's analyze a little bit more in detail what information bears the mean square displacement. Here we see a plot in which we see the mean square displacement as a function of the time, and the red curve illustrates the behavior of a sample in which no microstructure is present and in which the particles are free to move. In this case, we will see that the mean square displacement will evolve linearly with time, because as time elapses, the particle travel and cover the whole space in a diffusive manner. On the other hand, if we analyze the green curve and somehow a microstructure will start to develop which prevents the particle to move freely, we see that a plateau develops in the middle of the for average lag times, and this illustrates the fact that the particle at some point are kind of stretching the microstructure, and only after a certain time they will be free and they will continue their path. If, on the other hand, a strong microstructure is present, which basically means that the sample is starting to be almost solid, we will see that the plateau extends and the particles can't explore more than a certain distance, because they are trapped in the structure that imparts the solid behavior to our sample. So it is clear that this signal gives us a huge amount of information to understand the properties of our sample. And it is clear that the more a microstructure develops, the lower will be the plateau and the longer it will extend in time. Let's see instead what information we can gather more, what quantitative information we can gather more if we know the size of these tracer particles. Indeed, what we can obtain is the storage and loss moduli as a function of the frequency of oscillation. What are the storage and loss moduli? They are a measure of the stress that it develops in the sample due to either a deformation, the storage modulus, or the rate of deformation, which is the flow, for the loss moduli. And here on the left, we can see a graph of these two moduli in log scale. And for a solid, a viscous, a viscoelastic material. And we see that when the oscillation is very slow, which basically means that our particles, the frequency that we are observing is very low, our sample will have a modulus, a storage modulus way larger than the loss modulus. Whereas when which basically the loss modulus will be way larger, which basically means that behavior of the system in this frequency range is more liquid. On the other hand, if the frequency increases, we see that the storage modulus will increase, will become larger than the viscous, the loss modulus. And in this regime, the sample will show solid-like behavior. Instead, if on the right side we look at the plot of the moduli corresponding to a viscoelastic solid, like a gummy bear, we see that at most all of the frequency, the storage modulus will be much larger than the viscous modulus, which basically means that the sample will be solid, and only a very large frequency behavior is inverted, and the sample will start to show a viscous behavior. So here I give back the word to Coline Bretz.
Thank you very much, Andrea. So I think that now DWS has less secrets for you. I would like now to summarize how this instrument can be helpful for you. I want to precise just before I start that information about DWS can be found in many ways, and I will give you some resources at the end of this presentation for you to learn more about the technique. So I've mentioned before that with DWS, you can study samples in their natural state. Andrea mentioned it as well. This is because we use samples that are sealed, under which there's no evaporation nor contamination going on. And that means that this, combined with the contact-free nature of the DWS, where we shine a laser in the sample instead of deforming it, we can then perform tests over a very long time on these samples, whether we would load them and store them in a fridge for some months and then remeasure them after, or simply submit them to various conditions, increase or decrease of temperature. Various changes can be applied to the sample, but we can always remeasure them as they are in the cell, or for people who would like to be a bit more precise, in the packaging. Now, something else that is very important with DWS is how sensitive the technique is. And that is because we use very high quality optics in these instruments. With such high quality optics and fast detection with fiber optics, we can actually detect changes in the microstructure just as they start to happen in the sample. So if you're, for example, if you're studying a food system, let's say a yogurt, and it's decaying in time, and this decay might not be readily picked up by a mechanical rheometer, but it will actually be picked up by our RheoLab very easily due to the nature of the technique. Andrea also mentioned, and I want to emphasize this, how fast the measurements are. If you've ever performed rheology measurements using a mechanical rheometer, you know that this can be quite long, because to investigate the data at one frequency, you need several minutes, typically 5 or 10 minutes, to obtain the results, the G prime and G double prime, the loss and storage moduli, at one single frequency. With our RheoLab, you get a full frequency sweep, so the full storage and loss moduli over the frequency range available in less than 5 minutes. So that's 10 times faster than a mechanical rheometer. Something I also mentioned earlier is that you can load the cells with as low as
150 microliters. So if your sample is precious, this can come very handy. So you don't need to load 1 or 2 milliliters of the sample at once. You can use very, very few amounts. And you can also recover it after the measurements. You've seen that we use glass cuvettes, of course, provided that they are very clean, that you maintain them well. Nothing prevents you from recovering the sample and use it for another characterization method.
You can also measure particle size with this instrument in the range of 100 nanometer to 1 micron. And this is possible to do if the system does not have any elasticity, if it's purely viscous. So you get, with this instrument, both a rheometer and a particle sizer. At last, I want to mention that this is a compact and rather transportable instrument. You've seen in the video, the dimensions are 40 by 30 by 24 centimeters. And the weight of this instrument is less than 15 kilograms. So again, a solution that is very compact and transportable with a low footprint in your laboratory. At this point, I would like to mention a few examples of systems that can be studied using our DWS RheoLab. The first example is going to be a gelation process that was monitored with the RheoLab. And in this example, we are considering a system of gelatin in water at 2.5 weight%. And this system was undergoing a decreasing temperature ramp from 60 degrees down to 20 degrees. What we can see on the resulting mean square displacement curves is that at the temperatures between 60 degrees and 40 degrees, so the first 3 curves that you can see on the left side, is that the system is purely diffusive. The mean square displacement increases linearly with time, showing that the system here is purely viscous. It behaves like a liquid. As the temperature is decreased down to 32 degrees, we can observe as a consequence a decrease of the diffusion. So the MSD curve is slowing down with time. So the slope of this curve is decreasing, showing that the diffusion process is slowing down, and we start seeing the appearance of an elasticity in the system. This is confirmed by the next temperatures recorded. So we have 30 degrees in which the system starts to plateau, and at 20 degrees and 28 degrees Celsius, the system indeed shows a real plateau, mentioning and showing that the gelatin is now arrested. The system is in a frozen state. Again, the lower the plateau, the stronger the elasticity in this system. And you can see here how we can identify the gel points of this system by looking at the moment where the mean square displacement is no longer linear. In this case here, we start seeing this at 32 degrees Celsius. Of course, again, with our temperature precision settings that are lower, better than 0.02 degrees, we can monitor this process extremely precisely. Our next example is going to be considering an ink formulation. When formulating inks, researchers are looking to characterize the viscoelasticity at high frequencies. And this is because these systems, the sample of ink is going to be injected at very high frequencies through very, very narrow nozzles. The opening of the nozzles in consideration are typically a few microns wide. So it's very important that this formulation can go well through the nozzle and form inkjet drops that can be correctly printed onto the desirable material. In order to determine if the formulation can be jetted, we can look at the images that you see on the left side of this slide, in which you see the drop being injected as a function of the time. In the upper example, you see that the formulation was too elastic to be properly jetted. What happens is that the drop goes through and then bounces back against the nozzle. So we cannot generate actual inkjet drops with this system. And so this formulation is not jettable as the requirements would be. In the lower example, the formulation has the desired viscoelasticity and in fact generates drops. So in this system, the viscoelasticity was optimal and allowed for the correct jetting of this formulation. How do we know if the formulation is optimal. We can look at DWS measurements for which the high frequency behavior is indeed accessible. You can see on the right side of this slide the storage and elastic modulus measured by DWS at high frequencies. So we want to check that the loss modulus in red is always higher than the elastic modulus, and also that the elastic modulus is inferior to a certain given value that is determined by the experimental conditions and by the researchers. We also want to monitor the viscosity of this formulation, which you can see in dark. Something that is important to mention here is that in this case, the elasticity of the formulation was too weak to be accurately characterized with a mechanical rheometer. So this is where the sensitivity of DWS can be a real asset for your formulation development. So we can analyze the suspension both at high frequencies and if we have weak elasticity and viscosity. In our next example, we are looking at a gelation process inside a food protein system. The system in consideration was polydispersed casein mice cells that had been pre-steered prior to the insertion in the cuvettes. And we are looking at following the gelation kinetics over time. So we're looking again at the storage and elastic modulus, but this time not versus the frequency, versus the time. And we select this value of the storage and loss modulus at 1 radian per second, and we always follow it across the 30 hours under which the experiment was taking place. So what we see after the steering, and as we start to investigate the evolution of these values, the storage modulus is always under the loss modulus. The loss modulus is in the open circles, and the elastic modulus is in the filled circles. So we see that the loss modulus evolves much slower than the storage modulus. The storage modulus starts very weak and then builds up with time to cross over with the loss modulus at a characteristic time of about between 200 and 300 seconds. And this is where we can characterize the typical time for the structural arrest, which means basically when does the gelation start in the system. We can continue monitoring these quantities at a longer time and to see how the gel evolves. And so as you can see here, again, this is a sample that can be studied as if it were in its packaging. It's loaded in a sealed cuvette and does not undergo evaporation or contamination, which can be critical for such sensitive food protein systems. As we reach the end of our slides presentation, I would like to mention a few sources for you to obtain more information on microrheology. This webinar was a very introductory presentation for you. You will certainly want to know more about this technique, and we encourage you to exploit the sources mentioned here. You can look at our website. You can subscribe to our DWS newsletter. We typically release one edition every other month on a variety of topics. And you can also follow us on social media, LinkedIn or Twitter. And I really encourage you to read the book published by Eric First and Todd Squires on microrheology for a complete information on this technique. I would like now to hand the speech back to Andrea for the demonstration of our LSLab software.
So here you see the main window of our new software, which is called LSLab. This software was developed from scratch, leveraging on the best programming tools and technique for the Windows platform. So the main goal of the software was user-friendliness, and was user-friendliness targeted to a wide range of users, spanning from production technicians to advanced research in academia. The basic idea you see is very simple. The software starts, and we have a set of tiles. Each tile corresponds to a task. So we want the user to start the software and to be readily be capable of starting the task that corresponds to their needs. And to illustrate how we targeted many kind of users, we can illustrate how each tile caters to a different category of user. For example, if you are a science in academia and you are more or less involved in some preliminary measurements, and you want to do some casual measurements, you want to just to access the first tile, which allows you to perform single DWS measurements. Instead, if you are a production technician on a production site and you want to follow a certain measurement protocol very well defined previously, that's the run protocol tile that is fit for you. If you are instead a production engineer and you want to establish a certain protocol to be followed, for example, after a certain production campaign to test the quality and the outcome of the production campaign, then you will want to access the manage protocol tiles and to define a certain measurement protocol. If you are instead an instrument maintenance technician, you want to make sure that the instrument is always calibrated and you access the maintain instrument tile. What if you are instead or a quality control engineer, or if you are a scientist in academia and you want to compare the outcome of several measurements? That's the compare data tile. So after having said that our software is task-based, we want to show you how we wanted really to mimic the idea of a lab journal, and that we can do by showing the data browser. So in the data browser, you can see that in this line, in this first table, we show all the experiments that have been performed. What is an experiment within SLS Lab? An experiment is a collection of measurements, and those measurements have something in common: the scope. They belong to the same experiment that we are doing. And here you can see that in the second list, we are showing all the measurements that belong to a certain experiment. And since each measurement, and we are scientists and we want to test reproducibility, each measurement is made up of several repetitions, as you can see on the third list, where we can access each repetition. Each time we access a repetition, we can see the measured data. All this data is stored in a database, which basically means that we have a total traceability of our experiments. The experiments and the measurements will not be scattered on the hard drive. They will be lost, and they will be very difficult to access in the future. So here, really, the goal was that of creating a software that allows us to do tasks that produce measurements and experiments, and these experiments are then stored as a lab journal. Now, what I really want to see and I want to show you, for example, is the outcome of an experiment. Let's say, for example, that we have measured this gelatin, and we have measured it at 30 degrees. Here, this is a measurement, and we want to show you a result. And here we see the correlation function that corresponds to the gelatin that is almost reaching a liquid state from a gel situation. And we can see that the correlation function doesn't decay to zero. And this we see on the left graph, where the mean square displacement is plotted against the lag time. We can see that the mean displacement, as said before, plateaus to a certain value. Now imagine that we know the tracer particle size. We can input here, and we can see the moduli that correspond to this mean square displacement. And you can really see that as we said before, for lower frequencies, the storage modulus, which is the dark green, will be larger than the loss modulus, in agreement with what we said before. If instead we go to 60 degrees and we take one measurement, we will see the decay is complete. The mean square displacement is linear, which is with the lag time, which is a sign of of a viscous and liquid behavior. It's not plateauing to a certain value. And the moduli show that now the light green, the loss modulus, is way larger than the storage modulus, which is the demonstration that this sample is at this temperature liquid. Now that we have shown how the experiments are organized in this virtual lab book, I want to show us a key strong point of our software, which is the protocols. The protocols, many software that run instruments offer a text-based language to create protocols. Since we had in mind usability and user-friendliness, we decided to develop a fully visual language that doesn't require the user to be an expert in programming. And here I want to quickly walk you through the creation of an extremely simple protocol. Here we click Create. Then we want to create a protocol that corresponds to a temperature ramp. So we will call it temperature ramp. And we see that right away, the syntax check of our instrument protocol designer is telling us that several steps are missing. Because if we want to perform a measurement, we must be able to run a measurement, to specify the sample by means of the change sample, and to decide the temperature by the means of the change temperature steps. So where are the steps? The steps are all listed here, all the possible steps that make up a protocol. And in order to create a protocol, it's as simple as dragging the step on the right. So we decide to specify a sample, and we say that this is a test sample. Then we have to decide, we tell which cell thickness this test sample is stored in. And we are done for the need of specifying the sample. And we can see that the requirement of specifying the sample is the red balloon has disappeared. Then what we have to do is also decide the temperature. So we want to change the temperature. And we want to say that we want to wait for the steady state to be reached. And so you see that now the last requirement is to start, indeed, a measurement. And so we drag the start measurement. We say that we want to run it 30 seconds for the normal part, 60 seconds for the echo part of the measurement. We are good experimentalists. We make 8 repetitions. We are measuring in the transmission, and we check that the sample is turbid enough. And now you see that this minimum requirement of 3 steps is fulfilled, and no requirement balloon red is necessary. But that was not the goal of our protocol. The goal was that of looping over a certain increment of temperatures. So what we have to look for is a loop incremental. We drag it, and now this loop is a container. So we have to bring the steps of change temperature and start DWS measurement inside. So that's what we do. We move it until we see the insert, and then we move also the start measurement inside. And you see that now this is a single block that can be expanded and collapsed. Then we want to measure between 20 degrees until 60 degrees. And we are setting the start value and the end value in a step of 10. And we want to define this quantity as a variable that is called temp. Then clearly we have to use this variable. And you can see that in the temperature, in the change temperature, there is a small magic button that is like a chain that is broken. Now we click it, the chain is not broken anymore, which means that we want to connect to a certain variable. And here we find the variable that we have chosen before. So you can see that now the protocol is ready. The loop has been created that will go from 20 to 60 degrees, and there was totally no need to be an expert in programming. So I think once we are done with our protocol, we save it, and we can proceed to the protocol runner. And you will see that the protocol is ready for being used. We just need to enter an experiment name and an description. A last feature that is very important that I want to show you is the compare feature. So imagine that we have several experiments that we have done and we want to compare data. That's where this tile task is existing for. So we access our gelatin to 5% experiment. We take one experiment, we double click and we add it to the comparison. Then we go to the temperature where everything is changing, 30 degrees. We add another measurement and we will see that the correlation function is plateauing. And then we go to the first measurement at 20 degrees where the sample is very solid and we add it. And you see how nicely the correlation function can be compared. And you can also see the different behavior. The red is the viscous at the higher temperature. Then you will see the microstructure formation. And then you can also access the comparison of the moduli. So that's all for the software presentation. I give already again the word to Coline Bretz for the conclusion of the webinar.
Thank you very much, Andrea, for the presentation of the LS Lab software. If you would like to get more information on our software capabilities, you're very welcome to request a personalized demo through info@lsinstruments.ch. Now it's time for the question and answer session. We'll be having a discussion of about 20 minutes, and the transcript of this discussion will be released together with the recording of this webinar. So I invite you to submit your questions. And if you have more questions after the end of this webinar, please feel free to submit them to us directly via email. And at this point, I would like to thank you all for attending our very first webinar. We hope you enjoyed it, and we look forward to seeing you for another edition. Thank you very much, and have a very nice day.